some snacks, ready to go. Okay. All right. So with all that dramatic pause that I gave at the end, right, about maybe the whole first part was a little misleading. Well, it comes down to this. So I'll tell you my personal journey. It's actually around, I used to think the other part, first part, I still like the first part, was sort of where it's at, which is the idea is to take measurements and discover the models. Where I think I've actually ended up now, kind of years into this, is more here around, I call it manifolds and embeddings. It's just coordinates. Let's just call it coordinates. How do you take data that was measuring something, and you measured it again because you just had a sensor for it, right? You got a sensor, you put it on some stuff, you took some data. You may have an idea of what things are important, but at the end of the day, you're measuring something. And what you really want to do is discover a coordinate system. And I'm going to start this off by an example I like to give. First, I got to open my trail mix to give me energy for this last half. It's actually more like last 2/3. It's a long, we're in for the long haul till lunch here, right? So here's the example I want to give you. Alexander the Great storms through Persia, taking over the known really world at that time, right? He comes over, he dominates. If you ever want to feel good about yourself, like I'm doing awesome, just read about Alexander and what he was doing at 16, at 18, conquered the world. Like the dude was amazing, right? But then he died, and everything fractured. One of his generals was smart enough to say, well, we're going to go bury him in Alexandria. He took a little army, and then you could hold Egypt. So he basically set up a very stable place in Alexandria. And Alexandria became, in fact, the intellectual hub of the ancient world, above Rome. Okay? You had the Library of Alexandria. You had some of the best thinkers in the world. And out of there came Ptolemy. And Ptolemy is actually the general's name that took Alexander there. But you became this intellectual hub. And at that point, Ptolemy came up with this idea about measuring the orbits of planets. And this is the doctrine of the perfect circle. Perhaps you've heard about it. And the idea is that if I want to map out the motion of the planets, what it is circles on circles on circles, right? So there's this idea of the sacredness of the circle. And every single planet you would have there is just rotations of various sized circles that would map out its trajectory. Kind of like a Fourier transform, frankly, right? If you want to think about it that way. It's like a Fourier transform. Here's the frequencies I need. Those are all circles, and I can now represent anything in those circles. Now, I'm going to argue that that was, in fact, one of the longest standing theories ever, which was this is posited in the 2nd century AD and not taken down until about the 1500s or 1400s. Okay? People had the audacity to propose that, in fact, maybe we should put the center of this coordinate system, maybe the sun should be there. Okay? Now that was problematic, by the way, because having the Earth as the center of this circle-on-circle system was somehow viewed, right, as sort of this was the natural architecture of the universe. And making the sun the center, this new coordinate system, was highly controversial. Okay? You have no further to go than go to Rome, and you go to Campo de Fiori, and right there is a statue of Bruno, who was burned at the stake for holding his opinion that no, this is right, that everything goes around the sun, right? So it was not just a trivial banter. This was life and death, okay? Now, what wins at the end of the day is moving to that coordinate system. From Kepler, Copernicus, Galileo, and then you just take it off. Now, by the way, this is amazing because that was the beginning of the scientific revolution, right? So that coordinate system change, it was very quickly after that. Then also we have positive gravitation, calculus. The development of science from there was very important, okay? So I would say coordinate systems are really important for us. And in fact, if you look at a lot of physics textbooks, whether it's quantum mechanics or E&M, it's all about coordinates. And what I mean by that is if you look at a copy of Jackson's Electrodynamics, which is sort of the standard torture of a grad student in physics, most of it is about eigenfunction expansions and waveguides. And what those are the right coordinate system for those waveguides. Or in quantum mechanics, you look at the eigenfunctions of the quantum mechanical system as the right coordinate system. Okay? Now, in those cases, you're able to write down a model first and then find this coordinate system. And those are linear, so eigenfunctions will do fine. Okay? But when we go to measure some of these more complex systems, what we'd really like to do is do a little bit what was done for gravitation, which is, can we find this coordinate system under which all of it kind of unfolds for us, right? The natural coordinate system that we want to work in. So this is going to be the emphasis of this next section. And I want to talk a little bit more about what I mean about what a great coordinate system looks like. Okay? So let me paint a picture for you. Let me paint a picture. Hold on, what's going on here? All right, there we go. All right. We're going to talk about Bernard Koopman, 1931. The paper written. And this has become something that's become a hot topic in what we looked at. Koopman operators. So Koopman in 1931, he was working on quantum mechanics, and he started saying, well, okay, look. He wrote down this definition of what we call a Koopman operator. You give me a nonlinear dynamical system. Remember, this is what we were playing with before, finite dimensional, that there exists some function g of x. In other words, I have some observables of x, functional observables of x. In this new coordinate system, these new g's, the system is linear. And this is my linear operator. So this is kind of a staggering proposition. It says that I can take these nonlinear systems, I can just find that right observable, I can make this go from a finite dimensional nonlinear system to an infinite dimensional linear. Of course, infinite dimensions is difficult for us in practice. So we're going to have to make it, we're going to try to go from finite dimensional nonlinear dynamical system to a finite dimensional linear system if we can. That's what we'd really like to do. Now look at the time, 1931. Part of the reason we don't hear about this, didn't hear about it then, is he's got no computer, right? So you're kind of limited. You do pen and paper work, and that's it. So it sits there as an idea in the background until about 2004, 5, Igor Mesic, who's at UC Santa Barbara, started picking up the threads of this thing. And now with a modern take and with computational power, we can start going after these things. Let me change my slide order here a second. I'm going to jump to here. You won't even notice that I did this, but I will. I'm going to give you two examples of a Koopman operator. Here's example number one. So what you see here, right, is this is like a Boyson de Prima level problem, right? Little 2x2 ODE. It's got that nonlinearity right there. Okay? So what did you learn in Boyson de Prima? Well, if you had Boyson de Prima, like who took Boyson de Prima for ODEs? Like a bunch of you, like, and whatever. They're all the same. All these books had different authors, but really ODEs is like almost taught the same through all these courses. But when you get to the back ends of those chapters and you do nonlinear systems, what you do is you look for fixed points and you do linear stability about each fixed point. So you say, okay, I can linearize about a fixed point, get some idea of this, and then I can solve it with like ODE 4.5 to see the trajectories. Or I can change to a new set of variables. I'm going to go to y1, y2, y3, which are defined as x1, x2, x1 squared. I move to a new coordinate system. And here's what's remarkable. In this new coordinate system, this is a linear equation. Okay? Very simple example, but it shows you what we're after. My hope is that you see a couple examples I'm going to show you, which are just very clear demonstrations of like, this is the Platonic idealization of what it means to have a great coordinate system. Is I have a linear model. And by the way, why is that important? Because I can solve it. Not with a computer even. I can write down the solution on pen and paper. Like, solve it like when I was in, before computers. What it meant to solve something was to write down an answer on pen and paper. And I can do that with this. It's trivial. So you want to know the future state of that system, my pen and paper, I just say like, oh, just plug t as whatever. You want t as a billion? Done. Right? Where versus if I simulate it, I've got to run it to time a billion, which might take a while. Okay? So this is one example, and it's a little fake. What I mean by that is, it works, but there's very few problems where you can actually get this to work. A certain class of differential equations would allow you to close it. Most of the time what happens is it never closes on itself. What I mean by that is you don't get a finite truncation where everything is coupled together in this new coordinate system. Most of the time it just can keep defining new coordinates which make it go to infinity. Okay? And again, we have to stay away from infinity because in theory it works. There's a lot of things in theory that work. And then practice. So our goal is to make practice work, not just the theory. Let me give you one other famous example. And this is a PDE example, Burger's equation. There it is. This is the Burger's equation. It's kind of famous. It's so simple in a way. Like, I kind of love the elegance of the 50s and 60s because they didn't have the ability to do computations so readily. So they really kind of worked hard at these canonical models and things that you could do with pen and paper. And there's a lot to be learned there. And they did a lot with asymptotics. And what this was kind of in some sense the simplest model possible that captures some of the things that they were seeing in fluid dynamics, including shocks. So it was one of the things they were really trying to understand is how do shock waves get produced? This is at a time when we were learning about supersonic flight, and shock waves were a big deal. People want to understand, what were shock waves, right? When originally they were going to break the sound barrier, there was some question about what's going to happen to that plane and that pilot. As you get into the shock wave, is the plane going to explode, right? And I think that was their first thought when they heard that first sonic boom is like, we just lost Chuck Yeager, but he went through. There was a sound wave. So the theory is really important to think about. And what it does here is this is basically wave propagation, one-way wave propagation, where the speed depends upon the amplitude. So if you have a lump, it starts to form, like the top part of the wave is moving faster than the bottom, so you get a shock formation. And of course, this will create a discontinuity in the solution. So what you do is you add a little bit of what's called, this is diffusion, but oftentimes it's called regularization. We've mentioned that term before, right? Regularization is our way of making a problem tractable. Regularization is thought differently back then, but it still does the same thing, which is my solution is going to go, I'm going to create a discontinuity, which is mathematically what does that mean? So instead what I'll do, I'll add a little bit of diffusion. So as I get a really sharp front or shock forming, all of a sudden this is small, but then right at that shock it becomes big. And basically, as a shock forms, it prevents it from breaking. And so this is a perfect model. Now, it's proposed in, so it's been around for a while, and people were studying this and trying to understand shock waves from it. And you get all kinds of really interesting physics out of it, right? Including computing what would shock speeds look like, the fan that is generated off the back of that shock. So you get all kinds of really canonical understanding of physics out of this kind of modeling. Now, what was understood in Cole Hoff in 1950 independently, both wrote down a transformation for this equation. They said, look, here's the transformation. If we move from the u coordinate to the v coordinate, remarkably, the Cole half transform gives you, Jack, the heat equation, which is linear. And instead of having two terms, it has just one term. So it's more parsimonious. It's linear, which means I can write down the solution with pen and paper. Right? So this is fantastic because in my original variables, this is what's happening. But in this new variable, I can characterize everything. Closed form, write down the solution. So it's attractive about it. So the way to think about this is your Koopman transform. This is your g of x into this new coordinate system that made it linear. Okay? So my point in showing you these two examples is to show you what the unicorn looks like. Right? This coordinate transformation where everything like just boom, unfold. I can do everything now. And the problem with it is they're very hard to achieve. This is the 50s, 1950. Since that time, there's very few other PDEs we've been able to do this with. There is the inverse scattering transform, which solves KdV, nonlinear Schrodinger equation. Those you can do through this machinery of the inverse scattering transform. But aside those, you can't really list that many other PDEs. So it's a really hard problem. Part of it because it's hard to find a variable that can actually close on itself. Okay? But these do. All right. By the way, a more practical goal then, maybe with Koopman, is to say, like, you know what? I would actually just like to find a variable coordinate transformation where instead of making it perfectly linear, maybe I can make it mostly linear. What I mean by that is I want to really make it weakly nonlinear. So I want my nonlinearities to be small perturbations to the linear part. That's a realistic goal. That's an engineering goal. Like you could probably do that. Okay? That's versus a perfect embedding. Few problems will have it. Okay? All right. So this is Koopman. This is the idea. I can maybe move to a new coordinate system. Now you see what happened here when I did this. If I can do this, the whole first part of my talk, I don't need it. I have a linear model. I don't have to find nonlinear terms. I got a linear model. I can write down a solution, pen and paper. I don't have to simulate anything anymore. Here's my model. Write down the solution. Do you see what I'm saying? This is why I make fun of myself at the end saying, well, maybe that was a whole stupid idea, which is because maybe this is the better idea. Find that coordinate system, then I don't have to do all of the discovery because I just get the linear operator, write down solutions. It's that easy. Okay? Of course, it's not that easy, right? I mean, I say that, and I give you two examples. I'm telling you what I really want to try to do, and then I'm going to tell you what happens on my way to try to do this. Okay, so back to here. So this is this idea, and this kind of took off really around 2004 and 5. Igor Mesic started bringing this Koopman idea back to the forefront. And then something remarkable happened in 2010. Peter Schmidt. So Schmidt will be giving the talk tomorrow morning at 9, I think. He gives the first plenary of the conference tomorrow. And he was a faculty member here, actually. And he left just before 2010. And what he wrote, it was a paper called on what's called dynamic mode decomposition. What it was a way to approximate, give me snapshots of a dynamical system, and I'm going to give you the best fit linear model of that system. And what was realized from that paper by Mesic and Rowley and others was, in fact, that Koopman, let me go back to here, is that the dynamic mode decomposition was an approximation for the Koopman operator. Okay? So I'm going to just walk you through what dynamic mode decomposition does. It's a regression. And it's regress to a linear model. So you're going to give me snapshots of your measurements of your system, x1 through x of m. So I just measure my system in time. And I give you snapshots x prime, which is for each one of these snapshots, x1 prime is delta t later into the future. Now, if I'm on a clock and I'm measuring it every, 1 second, 2 seconds, 3 seconds, then x1 prime is actually x2, x2 prime is x3, and so forth. In other words, here's the snapshots. Here's all of them advanced delta t into the future. So what I want is a map that takes me from these snapshots and advances all of them delta t into the future, which is a matrix A. I want a matrix A that hits x and gives me x prime. OK? So right back to sort of solving ax equal to b type problems. OK? So a times x is x prime. So I could just take this matrix A. You could then say, well, OK, if I want to know what A is, I'm going to do a least square regression by just saying, well, A of x, well, I could multiply both sides by the pseudo-inverse of x, which is a least square fitting problem. And so A is x prime, which is this snapshot state, times the pseudo-inverse of that x. Least square fit. It gives me the best fit linear model for those set of trajectories. What Koopman was trying to do for me was give me a linear model out. So this is an approximation to the nonlinear dynamics. It's not necessarily going to work very well. There's no guarantee it's going to work well. But it is, in fact, a blunt instrument for giving me a Koopman operator. OK? Everybody good with that? So I will highlight this. This simple least square regression was work here from Jonathan Tu, who was a former UW undergrad. He went to Princeton and worked with Clancy Rowley, and then he and I and Clancy and Steve Brunt we wrote this paper on this, doing this least square fitting procedure. And the reason I highlight here Travis, ask him, is Travis came here for a postdoc, and we worked together on trying to make better this approximation. So what we did is we actually did what's called optimized DMD, which is a significantly better, it takes out a lot of the bias that you get in this what's called exact DMD architecture. So if you want the best method for a DMD fit, this is the optimized DMD. There's source code in MATLAB and so forth to run it. Okay? So again, what this is giving you is trying to get towards this issue of saying, I would love to find an embedding for dynamics where everything's linear. And again, it's obvious why I want to do that, because if I have a linear model, just write down solutions. In fact, if I have a linear model, once I have that A, all I got to do is look at the eigenvalues and eigenvectors of that A, and I'm done. I can tell you the solution at any time in the future. Okay? Of course, there's a question, here it is, right? So then if I have that A, well, there's my solution. It's an eigenfunction expansion, but now these are called DMD modes, DMD eigenvalues, and here is my projection. So now I can say, well, what do you want to know about the solution in the future? Just plug in the time you want. It's just an eigenfunction expansion at that point. Okay? So that's the concept. It's been really heavily used because it's a completely data-driven architecture, right? There's no model assumptions. It's just saying, you give me time series data, I'm going to find you the best model, and then let's look at what we can do with that. Okay? It's an embedding space that I'm going to work in and commit to. So some applications. I just give you a collection here of stuff that I worked on, and just show you a little diversity of stuff. So first, I did this paper with this guy, Jordan Mann, who was I was on sabbatical at Harvard that year, so Jordan was a student there. Dynamic for financial trading strategies. I'm actually like a billionaire because I traded off DMD. I just show up for this. This is just my goodwill gesture to the world. Okay. It takes a lot. You have to have, you know how they say it takes money to make money? Well, I didn't have the money to make money. But if I had, maybe I could have used it. So we just published it instead, right? The first thing you know is someone published a paper on finance. That means they didn't make money, right? Because the first rule of Fight Club, you don't talk about Fight Club. It's the same thing here. First rule of finance, you don't talk about your algorithm. You just shut up about it, okay? All right. But you could do that. You can also look at recordings of brain waves. And these were looking at brain spindles. This is from ECOG recordings. And you could slide a filter through there. You could start looking at these clusters of activity that happen on these brain patterns and looking at little sleep spindles that occur there. So it's a nice diagnostic tool for these really messy biological systems. And the other one that was kind of interesting was this idea of background subtraction in video. So if I take a video and I think about the video as a dynamical system, I can always ask the following question. If I decompose it into this solution that I showed you, I can ask you, what if omega k is 0? What does that mean? E to the 0. Well, that's something that's not changing in time, right? So what I could do is say, I'm going to run a video through here. And what I'm going to look for is, which mode has that 0 eigenvalue? And the interpretation of it is, the mode that's not changing in time is the background of that video. So you can start thinking about saying, well, OK, that's the 0 mode. I just pull off the background from the video. And what's left, foreground. Those are the objects of interest. Does that make sense? So it's a really nice, very fast technique for subtracting out. So now you can pull out all these cars that are moving. And because you're not really interested in the buildings and roads. You're interested in the things that are happening here. Okay? So it's a way to do video processing in some sense. OK. Another really important application of this DMD type architecture. So Koopman and DMD, like I said, they're intimately related in the sense that DMD is the algorithm that computes a Koopman for you, okay, at its base state. And it's the more practical, this is the engineering thing, whereas Koopman can stay up in sort of fairyland a little bit. And the idea is to bring them together a little bit, okay? Here is, I think, one of the most important pieces of DMD is DMD with control. Not only can you discover a linear model, but where this really matters, a linear model, is when you're trying to do actuation and control of systems. So when you're going to try to actuate a system, you might know what you're actuating with, which is the U over there. And you know your state space. And maybe you don't even know what the dynamics of that thing is, or even how, when you hit the system, how it's talking to X. So you can, but all control theory is framed in here as this: X dot equals AX plus BU. That is like the canonical framing of control theory, where we can get guarantees, behaviors, and so forth. So imagine what we have here. We have snapshots of the system. We also have snapshots of my controller. What you can do now is do this regression. But instead of regressing just to find A, you're going to maybe regress to find A and B. Or if you know B, you can just regress to find A. What this allows you to do is to disambiguate in your system what is a control and actuation from what is dynamics. Okay? Let me go back to the first part of the talk. One of the interesting things that has happened is people ask, oh, do you think you could discover, like, you know, I work in neuroscience some, and people are like, hey, what if we discovered the equations of the brain, right? What are the governing equations of the brain? That's something people would like to do. Except there's a problem with that. The brain is a massively actuated system. It's not like the brain is a dynamical system that's just kind of like open flow. Like, you know, it's like open loop. You just set it going and it does stuff. You guys are influencing me right now. My words are hitting your head and going inside and influencing you perhaps, right? So you're getting stimulus all the time, and it's actuating the system. The brain is much closer to this than it is sort of some open loop thing going on. Stimulus is always coming in. The brain is reacting. So it's like a giant control system. So people that ask, I always say, well, and it took me a while to figure that answer out, right? Because people are like, what if we discover the brain? And like, I didn't have a good response, but now I do. And it's on camera. So that's what you do. OK. And so this is an important one. So I'm just going to leave it here. I'm not going to talk about control systems so much. But for many of you who do think about control, especially in the engineering sciences, often if you look at most engineering departments, there's a set of courses that every engineering department offers without sharing. In other words, oh, it's the same course we're offering. No, they don't care. You offer your own, we'll offer ours. They're going to offer us mechanical, aerospace, so electrical. They all offer control courses. And they don't like partner with it. They don't go like, what if we just offer it all together? No, it's too important. They want to do aerospace control applications, electrical engineering control applications, Mechanical engineering. Why? Because that ultimately might be the most important piece of your education when you come out of an engineering degree, at least if you're going to do theory, is control theory. Because everybody wants to control something, right? That's what the bottom, that's the end game of the engineered systems, is the control of that system. Okay. So that's that piece. The other thing I want to talk about with some of the nice things you can do with some of these architectures is things like multi-resolution analysis. So there's a version that's called Multiresolution DMD. And why is this important? Well, I told you about, like, we're not very good at multi-scale systems. Yet a lot of systems we're going to go after in a data-driven fashion have a lot of time scales interacting. Okay? Brains, atmospheric variability. In other words, the grand challenge problems we face as a community, we are often going to be multi-scale in nature. So what's interesting about the DMD is it can very easily be set up with a windowing type system. We say, like, well, what's going on in this snapshots, these snapshots, these snapshots? In other words, I can zoom in and out in time to look at different physics at different time scales, right? And so this architecture is very much like a wavelet decomposition of sorts. And wavelets are really important practically because they automatically handle multi-scale structure, and this can handle that. I'm just going to give you one example of this in practice, which is this sea surface temperature data. You can download it from NOAA. And you know what it is it's a movie of, over a 20-year period of what happens to the temperature fluctuations across the ocean. I'm going to give you a better picture of it in a moment, a movie, so you can get ready for the movie. It's coming, okay? It's not quite Game of Thrones, but close, so close. Nobody dies even. I mean, it probably makes it boring, but still, we'll work with it. So here's the thing. When you look at this video, look at that 20-year fluctuations, there's some dominant structures that appear. The number one dominant structure is that. That's just the average temperature over 20 years of the globe. And of course, it's exactly what you expect. I want to live here, don't want to live here. And Seattle's got a little bit too much green on it for my tastes. I was, when I was a kid, I was right about there in Brazil, right? See that red? That was awesome. But then, moved up here. I was actually born up here in that blue region in North Dakota. That's super cold. I don't know how my parents well, okay, I can see how my parents said, yeah, let's go here. But then I ended up there. Okay, anyway, that's a personal story. The point is, that one's obvious. The question is, all the other fluctuations that happen in time are kind of interesting to think about. So if you look over this whole window, that's like your dominant 20-year thing. But actually, you might say, well, I'm actually interested in yearly variability, monthly variability. Those things matter. And when you do this decomposition, one of the things that's happening is you take this window and cut it down, is you see some interesting things. Buried in here are some really important physics. Like, for instance, right here, let me show you this mode C that occurs right there in 1997. Here's what that mode looks like. I've taken out all the other modes, and that's the mode I want. Here, I'll get it for you. Yeah, there you go. Okay, a little hard to jump over that thing. Okay, and what do you call that? That's the El Nino mode. So just by recursively, by the way, a lot of these techniques that look for correlation in data, like PCA, completely miss this. Why? Because in the grand scheme of things, it's a small energy compared to things that are going on here at that scale. So it's just buried way down there. But as you start cutting the window down, and you get the right time dynamics in the right windows, it pulls out as like, there's a huge dominant structure in 1997, and that's what it is. So you automatically find this El Nino phenomena. It was discovered at the end of the, Sir Walter Gilbert, I think that's who discovered this thing in early 1900s. He was shipped off to India to look at data there for the British. At first they didn't believe this was there, but he just poured through the data to find this southern oscillation that was going on. And again, with what we can do now with these data-driven architectures, you just put your data in, boom, you're extracting this knowledge almost instantaneously, right? You're pulling out key features versus I have to look at the data for the next 5 years I think I see something, right? This is the idea, is to sort of have this automated for discovery. All right. So this is dynamic mode decomposition. I will point you to a resource for this a little bit later. We have a ton of code available for this, for doing this kind of stuff. You just download, run, work with it. It's used heavily across a lot of disciplines now because if you don't have a lot of data and you got a small collection of data on a system and you might want to try to control it, this is one of your go-to methods. What else are you going to do, right? I'm not trying to ask that in a negative way. I'm trying to say that sometimes this is just your constraint. Yes, you would like to do better, but you just don't have the option. You don't have the data for it. You don't have more information for it. So this is a way to give you a baseline working model, okay? All right, but let's go back to Koopman. I collect data. And it's going back to the issue of like, yeah, but you're making a pretty big assumption, which I am, that things are linear, right? I just took measurements of some complex system with some unknown dynamics, which is nonlinear, and I said, okay, here are my data matrices, and those are my observables, and I just crush it through this linear regression and say, there's my DMD model. I have a model now, a linear model for that nonlinear system. It could be that that linear model is just bad, because this says nothing about how good the quality is. It just says I can do it. Okay, but it could be a terrible model. What Koopman says, and this is the route you might want to go, you say, well, remember Koopman was about an observable. So I'm going to posit some functions of x, and I can then take these data matrices and turn them into y prime, which are x run through this observable g. So it's all about the observable. And the observable is all about the coordinate. That's what I'm going to go after here, which is, and then I can construct two new data matrices, y prime, which are new data matrices, which are this x shifted through my observable function g. And then I do DMD on that. So the algorithm here is the same. I'm still going to use DMD as the engine. It's just that in this pathway, because I have access to maybe proposing some g of x's, I have the potential to make this model here superior to that model there. Okay, that's the goal. Everybody okay with that? That's the picture. All right. By the way, we go back to these pictures here again. So here's your function. Here's your g of x. Okay, that was simple. Here's your function. Here's your g of x. You go through here. That's your observable state to here, right? So both of these cases, I have this nice pathway to get you. And by the way, now my DMD model, in these cases, my DMD model is perfect if I go through this. It's not just an approximation anymore. It's like I have a perfect model. Remember, that doesn't really exist in practice. There's no such thing as perfect models. We can all agree on that, I think, hopefully. All right, good. So, it's interesting being in math or applied math is you're always working at these two extremes of trying to be perfect and trying to be practical at the same time, right? So there's really nice theory you want to develop, which typically assumes some, make assumptions about unicorns existing, and you can fly. If under those assumptions these things hold. And then you go to practice, which is like, okay, now I got a horse, and I can kind of jump, not very far. That's flying for me. And the horse is the unicorn. So like, that's what you live with, and you got to make things work there, if that makes sense. Was that too much? That was a little bit of a too blunt of an analogy. But if you could just roll with me on that one, we'll keep going. All right. Let me give an example then of a practical model. Here we're going to apply this kind of technique. Here's a nonlinear Schrodinger equation. I worked on it a ton in grad school, past grad school, faculty, like whatever. I spent way too much time probably working on this thing. Here's a simulation of it. So I just take this thing, I simulate it, and this is called a two-soliton, and you see it just breathes. Okay, fine. But this is a full nonlinear evolution of this equation. Now, what I could do is say, well, if I gave you that data, could you build me a model for it? Suppose you don't have the PDE that I give you. Well, you can say, OK, well, I'll just do DMD on it. In fact, look at that. I take my measurement is X, and I just do DMD on that. Here's my approximation and reconstruction. But if I knew something about symmetries and nonlinearity of the system, I might say, like, well, how about if I enhance my observables as x mod x squared x? Now, why did I do that? Because I knew it had this intensity-dependent nonlinearity. So just say I put it in there. And here is my DMD approximation on this new variable. And I'm going to show you the difference between these in a second. But you can see that they kind of look to the naked eyeball to be roughly the same. And what happens if I pick a bad set of observables, x mod x squared x, not with this extra term? Terrible approximation. Okay, so just extending your observability space with other things is, in my view, kind of a bad idea. Okay, which there's an extended DMD method which projects. It's kind of like a little bit like if you're familiar with support vector machine or kernel tricks, you project into high dimensional space with a bunch of new variables. But it turns out a lot of those new variables are bad variables. So you can cross-validate to try to get rid of them. But in general, you create a really high dimensional space. And, well, and you're cross-validating to get rid of things like this. But if I pick a right variable, look at that. Good things happen to me. And let me just show you the difference between the linear and the nonlinear. So here's my DMD model. These are the DMD modes. Here are the DMD eigenvalues. By the way, they're all supposed to be on the imaginary axis. I know that from theory. But if I pick this, check it out. They're just lined up on that imaginary axis. In fact, one way to think about if you've got a good set of observables, if you're trying to pick a good g of x will actually make that happen. You're not supposed to do that, right? Look inside the laser. There you go. OK. All right. There you go. And this is a bad one over there. But here's one thing I want to highlight. Here's the error difference between this nonlinear set of observables and the linear. Right? It's almost 4 orders of magnitude difference. So your naked eye couldn't see the difference, but this is 4 orders of magnitude. More than that, this is what's kind of remarkable. When I time stepped this thing, I was using OD45 in MATLAB, which has an error tolerance typically around 10 to the minus 6. I'm right here at the boundary of numerical error just by using the right variable. So I almost nailed it perfectly, as good as I could numerically, frankly, just by choosing this variable set. So it tells you a little bit about having really good, if you can find good choices, and often this comes from expert knowledge of the system. Again, how much information do you bring to the table? The more you can bring, obviously you leverage it. Okay? But there's still got to be a better way. How do we do this in a more principled way? There, I kind of knew a lot about this equation, so I could kind of get away with good choices that way. So, we're finally going to do something nonlinear. Everything's been linear algebra to this point. Okay? And by the way, you saw we could get pretty far, which is linear algebra. So I think there's something to be said there. Start easy, work upwards. Okay? But we're going to move to neural nets. I guess I have a lot to say about neural nets. I won't say too many things about them here in this talk, except for the fact that they're widely used now. But I think there's a lot of bad uses of neural nets going on. I think you have to be very careful about what you're going to try to do with a neural net. What I'm going to do with a neural net is use it in very targeted ways. I am not putting my neural net in charge of an end-to-end discovery process. I also want to make this following point. Stéphane Mallat, amazing guy out of France. First sentence of his paper, Understanding Convolutional Neural Nets. Supervised learning is a high-dimensional, there's that word, interpolation problem. Neural nets are going to be great as long as you know that you're interpolating and you have enough data to do so. If you don't, you should understand that you're going to have a lot of problems with neural nets. Okay? And you have to be careful with any kind of claim you're going to make about them. Okay? All right. So what kind of neural nets do we have? Well, there's all kinds of neural nets out there. Here's the neural net zoo. Like you have recurrent neural nets, autoencoders, variation autoencoders, reduced base. Anyway, okay, a ton of architectures. A lot of these architectures, do you remember when we started talking last time about the F and the G? F is the easy thing. Like I want to build a model that does well with prediction. Like, okay, that was an obvious statement to make. We all want that. That's your F. The G is the regularization, the thing that's going to allow you to get there. To some extent, you can think about all these architectures as imposing some kind of form on G, this regularization. And the regularization, I made the comment, I think is the thing that carries the day. How you choose to regularize a neural net matters quite a bit, okay? They all carry assumptions in with them, okay? But first, before we get too carried away, what I did want to show is a very simple use of a neural net for dynamics, okay? And it's a little MATLAB code. I'm just going to walk you through it. Here it is. I'm going to simulate Lorenz. There, I'm going to pick some time steps, 0.01. This one I want to save my data. I'm going to run it for 8 units of time. Here's my Lorenz model. This is just OD45, right? Nothing. So first part of this code, OD45, simulate Lorenz. How easy is that? Really easy. Second part of the code is saying, OK, tell you what, let's simulate this 100 times. And each time I simulate it, I give it a random initial condition, run it through this Lorenz model. And what I'm going to do is I'm going to start saving the data that comes going from 0 times 0 to 8 at every point, 0.01. And I'm going to save, I'm going to look at what happens at time t, and how does it map to time t plus delta t. OK, that's it. So I save my data in snapshot pairs of t, t plus delta t. And here's how you do it. The input, output. Input is here, which is you take the first to the next to the last time snapshot. The output is the second snapshot to the end. So you're just lining them up in pairs. This leads to this, leads to this, boom. OK, that's my data. I'm going to collect data on 100 trajectories. And here's what that looks like. These are random initial conditions. Run it 100 times. What can I do with that? I want to train a neural net to learn that map between time t to t plus delta t. Look how easy it is. Make a network, feed forward, 3 layers of science 10, 10, 10. One of them will be a log sigma function, radial-based, pure lid, train. That's how easy it is. I just made this stuff up. I don't know. You can make more layers, less layer. Like, it's that easy. Go. It goes. It trains a neural net. And what does this neural net do? Well, it's going to give you back a function net that if you give it an input, it'll give you an output. So if you give me something, it'll give you that something delta t later into the future. OK? It's kind of as easy as that. PyTorch is as easy as this. So is scikit-learn and Python toolbox. So it's just going to just learn a map. Now, what are you really learning? What I say you're learning is just an integrator. There's no magic here. When you do Runge-Kutta fourth order, you can think about that as a neural network. It's got 4 stages in the middle. You carry the thing down to the end. So you can think of that as a neural net. But this just goes from my state space to 10 back to 3. I mean, who cares? It's learning some weights and some functions, just learning a new integrator. There's no magic here. There's no learning even. It's just like learning a map. Or it's fitting a map. OK? How well does it do? It does pretty well. What I'm showing you here now is I just picked 2 new trajectories. I've got this network train, and I just randomly picked 2 initial conditions. And here they are. The blue is running the neural net at a very refined time step. And so that's the orangish, yellowish thingy. And then the neural net is the blue. So it just learned a delta t map. Now I can simulate this thing or just run it through my neural net in the future. Here's some trajectories. So it kind of sticks this thing really well. Here's what's kind of remarkable, by the way. My time step for OD4.5 that I use for training was like 10 to the minus 4. I saved the data every 0.01, like 10 to the minus 2. Okay, that's when I saved the data, but the actual time step it took was much smaller. What's remarkable is this thing learns a time stepper at the time step of 0.01, because that's what I gave it to the data. And if I were to give it Runge-Kutta at time steps of 0.01, so Runge-Kutta, it's actually solving the actual model, like it knows what the model is. And if I run it, it will actually fall off that sooner than the neural network. It does worse, which is kind of remarkable. But really, maybe not. At the end of the day, I've given my neural net lots of parameters and lots of freedom. When you do a Runge-Kutta, what you do is you say, it's a bunch of Taylor expansions, and I use the Taylor expansions to kill off terms so that the error at every step is delta t to the 5th. Right? And you can work this out once in your life. Like, do Taylor's expansions and just cancel terms, and you'll get Runge-Kutta 4th order. Here it says, well, you actually gave me a bunch more freedom than you gave this Taylor expansion business. You gave me 3 layers of 10 nodes each. I've got a ton of freedom, and I could probably just keep crushing out the delta t to the 5th, the delta t to the 6th. It just can knock out higher terms. It does a better job than your integrator, which is 4th order Runge-Kutta. Okay? So just have that in mind. There is no magic here about the neural net. It's just learning a better integrator. So when people talk about like, oh, look, my neural net learns stuff, it did a fitting to a time stepper. Don't believe anything else they tell you. Okay? Please. Because there's a lot of magic words being used around neural nets that make me uncomfortable. I think they do believe in unicorns, maybe. And I had to tell them that, like, dude, that's like a donkey with a horn that you glued on. Okay? All right. So we want to use neural nets in a different way here. Remember, we're about coordinates now. And what I want to think about doing here is building a coordinate system for this thing. So here's what I'm going to do. I'm going to use a neural net. Remember how I was trying to find the g of x? Can I use a neural net to do that for me? So here's the idea. This is with Bethany. Bethany is not here. She's around this week. So you'll see her at the conference tomorrow and so forth. She's kind of awesome. She's at Argonne now. And so what we did is said, OK, let's try to do the following. I start with an original variable space x. And what I'd really love to do is move to a new coordinate y. And what do I want to have happen in the new coordinate y? Right, so I come into the space, I come out of the space. And I use a neural net just to learn a map to this new space. And what I want to have happen in this new space is when I go from y of k to ykf plus 1, which is one step into the future, I want this to be linear. That's the idea of Koopman, right? Just say, make that linear, take multiple steps, whatever you want to do. I want to do this, OK? And the example I'm going to give is let's try to just train it on a pendulum. Like the simplest physical model possible. I start off in x space. The equations of the pendulum are x double dot equals sine x. It's nonlinear. I'd like to move to a new variable y where it's linear. Now, here's the other thing. What's the dimension of that pendulum? Right? It's always two-dimensional. Theta, theta dot. Even when it's fully nonlinear. So you know the intrinsic rank of that thing is like 2. Now here's what's interesting. I can easily train a neural net to make this thing work if I just go this way and this way. But I know the thing is two-dimensional, so I want to keep it that way. I want to do physics, so I want the understanding that comes with it. So when I move this to this coordinate, I want this to work, and boom. You fail. Now, I like to bring up failure stories in regards to neural nets because I've failed so often that I don't want you to be too discouraged if you fail with it, because it's part of the game on this one is you're going to fail a ton. And we failed for a long time. I'm going to tell you why we failed, because it's only, I say this, but we could only come up with that 9 months later. It's like, oh, that's why it doesn't work. It was so obvious after the fact. So I'm going to give you a little picture. And by the way, I love this picture because, or a picture or whatever sketch. You see this? This is my scanned notes from graduate school in the 90s. I was writing this stuff down, and I thought this was worthless knowledge. Like, we've moved on. I've moved on with my life. What am I going by? I've moved on. I'm a new man. And it turns out grad school came back and said, wait a minute, here's my notes that I had. Like, you know, they were just inventing LaTeX back then, right? It's not even LaTeX, it's just like handwritten. And we were doing asymptotics and perturbation theory. And you could say, okay, let's go to the pendulum. And what did I learn in grad school? I learned in grad school that the pendulum isn't just y double is equal y. There's, the first term that comes in as a nonlinearity is this y cubed. That's the Duffing model, right? So people understand, what does nonlinearity do? Well, you can do this and think about that Duffing. And then you can do this Poincare-Lindstedt type expansion. This is an asymptotic technique. And asymptotics are something that's, I think, kind of lost on people today. We don't teach a lot of it as much as we used to. But one of the things you find is that nonlinearity does two things. It shifts frequencies, and it generates harmonics. And if you do this model here you go. There's the frequency shift. There's an epsilon in front of there. You get an epsilon frequency shift, and you generate harmonics. Okay? And you know this, right? Because as you swing the pendulum, it gets bigger, the period's changing. It's going to longer periods. So you already know there's a frequency shift there. The harmonics are being generated as well. And if you get bigger swings, you get a fifth harmonic. So let me just show you a spectrogram. This is actually numerical simulations of this Duffing. As you just increase here, this is the amplitude of the swing, and these are the frequencies. Notice what happens. Here's your baseline frequency, and what's it doing? Shifting. Here's the generation of that third harmonic. Can you see the fifth right there? Can you guys see that a little bit? So if I want to represent this in this new space, look at all the frequencies I need. I can't do it in this new space in 2 dimensions. Because look, I've got to span all of these frequencies. In fact, I need the entire continuous spectra to get this right. Which is obvious after the fact that what we were trying to do wasn't going to work. Okay? There's a fix, however. A patch, if you will. Let's do that problem again. But instead of just saying, let's move to the system where it's linear, that linear matrix that's there is going to be parametrized by the frequency. If I know there's a frequency shift, I want to say move into this new coordinate system and carry a label with it, which is the frequency. So I'm going to learn that this operator here, this is my Koopman operator, is omega dependent. Okay? That's the idea. So now I still have a simple linear operator, which is 2-dimensional, 2x2 operator, but it just has a omega dependence. So I can keep it 2-dimensional to get this thing to work. And so what it allows you to do, after you train, here's your training, blah, blah, blah. Put that in TensorFlow, go. It's not quite that easy, right? It takes a bunch of time, and you pay bills on training neural networks sometimes. And you take this, here's your nonlinear pendulum. Here are the oscillations, fully nonlinear. And this is what they look like in the phase plane. And what we can do is basically move all this into this coordinate system here. And here are your 2 eigenfunctions, as it were. And your dynamics now live on circles. This is a linear model now. So I've moved everything to a linear space. I have the Koopman embedding of the pendulum. Okay? And I've explicitly handled the frequency dependent, which allows me to do it. So one of the things I also find fascinating is that people are trying to solve really hard problems with neural nets. And I would argue that they don't know how to solve the pendulum. And then you could ask the question, what business are we doing trying to solve these really hard problems when we don't have the answer to the simplest ones out there? Because this really highlights for you a lot of the key issues around what you're going to have to address to do real physics. Okay? Now, if you're at Facebook and Microsoft or Amazon, you're not really, understanding learning and understanding physics is so secondary or tertiary, right? You're interested in 99%, improving your prediction accuracy, that makes you money, right? If you can improve your prediction accuracy by marginal percentages, it translates into a lot of money for them. So it's secondary. Like, you could solve this pendulum easily just by building a neural net. And what you're really doing by going up in a big neural net is you're saying, like, fine, I'll just build a Taylor series expansion with all these frequencies. Who cares, right? Is that a solution? Sure. I mean, you can make it work. Did you get the understanding you wanted out of it? Maybe not. Okay, so it depends on what side of this game you're going to play on. But at least here, I'm trying to emphasize more of, if you're going to come to try to use these methods for physics, for engineering, for fundamental understanding, you got to come back down to these simple things to get the interpretations, okay? So, you know, there's this big push. I don't know if you've heard these words like interpretable machine learning. Have you guys heard that? Generalizable machine learning. This is it. This is the kind of stuff. This is interpretable, it's generalizable. This is the kind of stuff that you're kind of needing to go after, I think. By the way, you can do that flow around the cylinder problem, same thing. Take that thing, flatten it down to a linear space. Okay? Yes?
So, like, for example, this example that we have here for the labs that we already have a solution that we can explicitly program a computer to give us a solution, right? My understanding was like net for deep neural nets and stuff like that are for problems that we cannot explicitly program. For example, detecting objects in a picture or face recognition, things like that. So can they argue that actually this is not the path forward for these stuff?
Yeah, I mean, okay. I would say that a lot of the people using a lot of deep neural nets are just starting to come over to the physics side of the world. Right? So you brought up some of the physics examples versus images, speech, non-physics-based models, right?
The problems that are easy for humans but not easy for machines. But these problems are easier for machines than humans.
Yeah. I don't know what to say about that. Yeah. We'll debate it at lunch. Yeah.
As you mentioned, you've spoken really all neural net with a lot of different variables. You would just need spending a Taylor series to why not just do that, right? Like, in order to
well, yeah, so good question. Why not just do that? Why not just go up to scale? And I would argue that it comes back to this idea, which is the pendulum is two-dimensional. And once you do this, you're committing it to be very high-dimensional, right? So.
Yes, I'm on board with the project of I want to find dimensional coordinate space, right? But in order to do that, why use a neural net at all?
For this training, like here?
The example you just gave.
Yeah, because we don't want to find it otherwise, right? I mean, okay, we could have potentially said if we know the exact solution for Duffin, which we have in terms of what we call Jacobi elliptic functions, but the minute you have x double dot sine x, you don't have any kind of analytics you can say to build that transform over to the new system. So, yeah.
I still don't understand the difference between a neural network and a boosting algorithm. Because like my understanding is they're both iterative and they're trying to improve their previous performance.
Boosting in terms of what? That's a very broad.
Like in terms of what like I was stats transient,
So I think of boosting as taking a small subsample, building a model, then taking another random subsample, building another model, and averaging these models. So typically, like a lot of the machine learning boosting algorithms are based upon things like this. Here, you just throw everything in, right? And presumably, I mean, where these really shine is if you have a lot of good, high quality data. Neural nets are going to. By the way, let me just say this about neural nets. If you have an interpolative setting with a lot of data, there is nothing that's going to beat a neural net. It's game on. It's going to get you to the 90 whatever percent. There's nothing that can beat them if you have that kind of problem. Okay. Yes?
One thing I wondered is, so is it possible to use the procedure from the first talk to actually find the transform?
Hey, let's get to that.
Oh, is that
I'm going to finish this section off before we talk about sensors by this title, Relax Koopman. It could be said like, hey, relax Koopman, or I could say, relax Koopman. There's a lot of different ways to say this that have different meanings. So what I mean by that is this restriction of a linear operator is tough. I showed it work here, but we had to work really hard at making it work. I also made the comment earlier that, like, well, what you really want to do is map to a system where you're dominated by linear terms, like so weakly nonlinear systems. So what we want to actually do maybe is say, what if I not throw away the first part of my talk this morning and say, well, let's take that Cindy idea and tie it into what I'm talking about here, a coordinate idea. And I'm just going to highlight one piece of work here done by Kathleen Champion. She's going to talk on Friday at the workshop. She'll give you the details of this. So if you're interested in this, she's the expert. She'll be around, staying around here at UW for another 6 months or so. She just graduated on June 3rd. There's her defense date, and got hooded last weekend. So here's what we're doing. Let's take this idea of building a coordinate system, but instead of this coordinate system having linear dynamics here, I'm going to say this coordinate system should be, in fact, sparse dynamics. So my objective function, or the loss function, is to say I want to learn a low-dimensional representation, a new coordinate. In that new coordinate, it doesn't have to be linear, but it should obey some Cindy. So here's the Cindy algorithm inside that new coordinate system. So I'm kind of bringing together what I think of as the best of both worlds, right? Which is I'm not going to restrict it to be linear. That's a super tough assumption, really tight to make happen. I'm going to let it be nonlinear in there, but parsimonious. By the way, this is nice because this gets you into, I want to write a paper called The Age of GoPro Physics, right? Which is you just film stuff and go. Like, I want to discover physics. So, I don't know, hang out at the mall sometimes. I mean, that sounds bad. Because my daughter's shopping, so I had nothing better to do. But you know where I end up always wandering to is, there's always like some camera shop which playing GoPro reels in the back, some people doing crazy stuff. It's kind of awesome. You go like, oh, I wish I was young again. Anyway, that's what I do at the mall. Because I'm too old to eat at the Cinnabon. Just effect right here. So I go there and watch these GoPro films. But what's interesting about the GoPro is you can start filming stuff and doing physics with it. Okay? It's a lot better sensor than most things. So let me tell you the canonical example here. What if I filmed a pendulum? When I showed you the pendulum before, we had to attach that Arduino. It pulled out the accelerometer data. It already knew about theta, theta dot because it was attached to that coordinate system. Now I just put my GoPro to look at a pendulum doing this thing, right? So if it's just watching the pendulum, the GoPro is just watching the pendulum. It doesn't know about theta, theta dot. Now, when you look at a camera and you see a pendulum in a picture, you say, like, that's a pendulum. And you already have the coordinate system in your head, right? You've done a lot of homeworks. You've seen pendulum. So you already biased yourself to saying there's a theta, theta dot in that coordinate system. Here, it's pixel space. Your camera has no idea what it's looking at. It's just like a bunch of pixels changing their weights, right? So the question is, if I just gave it a video of a pendulum, could it first of all discover that there must exist a theta, theta dot? And could it discover that it's theta double dot is sine theta on that coordinate system? Right? That's the idea. That's what Kathleen did. So the answer is yes, yes. You can do that. So it gets you to a thing where you can discover the right coordinate system, even though you lived in pixel space. You didn't know about theta, theta dot. This thing found it for you. Why? Because it says you need to find me a coordinate system where the dynamics is parsimonious. And the only way to do that is to build theta, theta dot, and then find theta double dot equals sine theta. They come in a pairing. Okay? So if we took this technology and we time travel back, right, to Kepler and said, check it out, Kepler, put this on your data, what it would have done is said, no, okay, here, first of all, let's move the coordinate system to the sun, and then on that sun, it's x double dot equals ma, right? F equals ma. That's what it would have done for you in an automated fashion, okay? That's the idea of this. So I like this because it feels like it's the right thing. It's trying to, for a lot of these systems, I'm going to go with biology as the canonical example. For me, biology is this crazy space where there's really exciting stuff going on in it, but we don't have, you take calcium imaging of all these brain waves going on. What's the right variable? We don't have an F equals ma type understanding of these systems yet. But we have these amazing data sets that are coming out of biology, but we don't even know what the right variable representations should be, especially at the coarse grain level. We understand what a single neuron does, but they're measuring whole brain activity. Are there governing principles there? I think it's an actuated system, but also, what's the right coordinate system for that thing? This is kind of trying to get towards that. Okay? How are we doing on time? By the way, what time am I supposed to end? Anybody have a program with them? Is it 12:30, right? Okay. You guys are being great. I wouldn't want to listen to me for this long. So thank you. I'll thank you ahead of time. I want to hit the last piece of what we want to talk about. And this is this idea of measurements and sensor. Remember, so now we've hit two things. We've talked about the discovery angle, which is taking the data, deriving governing equations. We've talked about coordinates. Maybe from the data, from all these measurements, can I train a system to figure out what the right coordinate system should be in the first place? Those are two important aspects that need to be brought together, and it kind of were at the end. By the way, all the stuff I'm talking about is sort of, I don't know, state of the art sounds overblown, right? But it's kind of, this is the kind of what's going on now. It's not like we've done this all. There's a ton of open road there for new stuff, new data sets, new exploration, of giving you a hint how some of this can work. Even the last slide, this just went up on the archive like a month ago. It was brand new. Like we're just figuring this stuff out. There's a lot of room for improvement and development. Okay? But brings us back to sensors, which is at the front end of all your systems. You're measuring and you're placing sensors. And the question is, what are the possibilities around that? Right? Because you're going to use that data to start building your models, to doing discovery. I like to start off with this cartoon here. I'll let you read it. Okay, I'm assuming everybody's about done. So this is kind of funny. This showed up in Krithika. You see, I brought this in. Krithika, I'm going to feature some of Krithika's work, who's in the back here. This is what we try to think about doing, is how do you measure systems? Because you don't have access to all the whole state. You're going to take a limited portion of measurements. And this appeared in the paper 1 week before a conference. I was just going through the Sunday paper, and there it was like, oh my gosh, this is what I work on. So I could work at his firm. So specialists try using math, which that's probably the smartest thing the boss ever said, right? And Dilbert, you can tell that he got his degree, a little bit earlier because he didn't know. I don't know how to do that, right? But we do now, actually. There's a lot of technologies around this now. It's okay, so don't be uninformed. Now you have the math skill. I'll write you a letter to go to that engineering firm if you want. It's a super fun place, super functional, okay? All right. So what is the idea here? This is kind of a crazy concept. How can you measure something so sparsely, let's say at 1%, and have it inform you about the entire rest. That's remarkable. Okay, it's going to go back to AX equal to B. And I'm going to highlight this here, which is this concept of what's called compressive sensing. And this is a simple, well, okay, it's a simple AX equal to B type problem architecture, which we've already talked about. And what it does for you is says, look, here's what I'm going to do. I'm going to take measurements of a system. Okay? And I'm going to measure a large state space with a small number of measurements. And what I actually have here is a problem that's ill-posed, just like I talked about it before. The beginning of this thing. This AX equal to B I'm going to tell you about, you can't solve it until what? You make an assumption or you provide a regularization. And the assumption I'm going to make here is whatever I'm measuring, there exists a coordinate system in which this thing can be represented sparsely. Okay? What do I mean by that? Well, let's go to your phone. If I were to take a picture of you with this phone. Now, this is not even that good of a phone, but this HD camera has like whatever, 2048 pixels this way, 1700 this way, plus it's RGB, so it's 3 levels. So you can just look at how many pixels this has. It's an enormous amount. Okay? Lots of information. The phone doesn't save all that. The first thing the phone does is throws most of it away. First thing the phone does is say, take the picture, put it into a wavelet basis, and let's just say I have 1 million pixels. It says, here's a wavelet, million wavelet coefficients, and guess what? All those million wavelet coefficients, almost all of them are 0, or very close. They're like so small, I'll just throw them away. In fact, in the wavelet basis, I'm going to keep like 1% of the information, throw everything else away. And that's what it did. And it keeps it there until you come to your phone and say, check out this picture I got. And you pull it up to show somebody and says, oh, OK, you want to recall it now. I'll take that 1%, pop it back up into the pixel space. We're using the inverse wavelet transform, and there's your picture. It's called compression. This whole thing works, all of our modern technology on compression. This is just a decompressor and compressor of information, right? Otherwise, if we didn't have it, you wouldn't have your iPhones. Or you'd take like one picture and be like, oh, it's loaded. Until I delete this photo, I can't use my phone. In fact, we just load stuff everywhere. Everything's compressed. So the whole idea here is in the wavelet basis, that image is compressible, which means, so here was the idea of compressive sensing originally. Well, if I'm going to take a picture and the thing I know I'm going to do right away is throw away 99%, why can't I just go grab the 1% that matters in the first place? That's the idea of compressive sensing. So what it assumes is I have a basis. Here are the bases, phi. And in that basis, I have a sparse representation. There's only a few wavelet coefficients that matter, a handful. By the way, do you see this? This is a vector with mostly zeros. It's right back where we started with that Cindy regression. I have AX equal to B, and I'm going to promote sparsity again. So what it does is you solve AX equal to B, and so here's how it works. I have a low dimensional measurement. X is the full dimensional, high dimensional state space. And I have a measurement matrix. So I take some measurement of y. And typically, this is a point measurement. So like, for instance, in an ocean, I put down sensors in point locations. That's this. This tells me where I measured the full state space. So maybe this full state space is trillion dimensional. And I took 1,000 measurements of it. So this is a map between 1 trillion to 1,000. And this tells me where I took those measurements. But this signal could be represented sparsely in some basis. So I can say, well, X is represented in some basis. This is the basis in which it's sparse. So, right? So I want to find A. So this times this is just a matrix. And this is just AX equal to B. Promote sparsity on A. I want most of those coefficients to be 0, few non-zero. So this allows you to get after this sparse measurement trick, which solves the Dilbert problem, which is I can take small number of measurements and reconstruct the entire ocean from those measurements. Okay? Let me come here and do, okay, okay, all right. So there's Krithika, and she's right up there. So you could talk to her more about this afterwards. And what's remarkable is, in some sense, how easy it is to do this in some sense. In fact, there's a MATLAB code for picking out best locations to measure a system. So again, you could say, well, okay, there's two ways to handle this. Suppose I wanted to start figuring out how to best measure the systems, but I have a large state space. So first of all, I'm going to take my model. I have full state estimates, for instance, for a bit. I take snapshots of that thing. Or I look at the basis representation of this thing, the low rank basis. And I can just say, like, take it through what's called the QR algorithm and look at where the pivot points are. What it does is it looks at this thing, looks at where the maximal variance points are, and says, measure there. That's kind of the ballpark way it does this. There's kind of a nice history of this, by the way. It goes all the way back to Everson and Surovich. They're the ones that first started thinking about face recognition. They had this whole paper on what we call eigenfaces. And that really started the computer vision community going. And that was just a PCA analysis of faces. And then they wrote this paper in which they said, well, can I measure sparsely along the face and reconstruct the face? And you can. That was what this paper was in '95. And then it started coming into physics 10 years later with Karen Wilcox and then others, including us, where he said, like, well, OK, so if that's the case, I want to measure physical system like fluid flow, ocean dynamics, whatever happens to be, and I'm at a small number of locations, but I want to reconstruct, I want a global estimate of the whole system from a small number of measurements. Okay? So there's a whole history here, and some of these techniques were very costly and expensive, and then you end up down here where this QR just gives you amazing results pretty quickly. Very nice methodology for doing it. By the way, I want to show you one cool example of this. I just have to show you a movie. Remember I said I was going to show a movie? Here's my Game of Thrones movie. Which is, what you're seeing here is the global sea surface temperature dynamics. And you can see the time scale of this thing. Okay. Now it's in 2000, 2001, and so forth. So first of all, you see the yearly fluctuation there. And the thing that's interesting about this data set is there are certainly patterns that you see there that are common. Come on. No, sorry. Go. Run. OK. No. Let's see if I can play the movie again. Is that playing? Oh, good. OK. So you can see there's some scale patterns. Look at this. That's kind of a cool thing right off of here. There's really interesting dynamics every places. So here's what Krithika did. She took that. She can correct me if I'm wrong. But she did a multi-scale, multi-resolution dynamic mode decomposition, pulled this thing apart, started looking where to place sensors based upon the dominant structures of that using this QR algorithm. So what you're seeing here is sort of, here's your multi-scale decomposition. This is like your wavelet decomposition. And then you ask, where should I place the sensors during different points of time so that if I measure there, I can reconstruct the entire global dynamics of that ocean. And so what you're seeing is these sensors. Is it going? OK. What you're seeing here, the color of the sensor is essentially the time scale, from blue being a slow scale, red being hot. And these are the locations that if you place them there, you can construct the entire ocean dynamics from those measurements. OK? So what's remarkable is how few sensors you need at any one time, right? So You know, over here you got 2, oftentimes maybe up to 5. And of course they're changing location, so that's an issue, right? You don't want sensors moving around the ocean. But the point is this. From a very small number of measurements, you can reconstruct this dynamics. You can even do a histogram of where all those sensors were and find that, oh, there's spots they can kind of around where they come back to. And so you might be able to say, like, from that, here's where you should put 50 sensors down on the ocean to reconstruct the entire thing. That's one thing you can think about. The other remarkable thing is, look how many sensors were near ocean shorelines. There's a huge cost savings to put a sensor on the coast versus having to park sensors in the middle of the ocean. So these are the kind of things you can do with taking data and using these optimization machine learning type algorithms to tell you, like, this is where you should be measuring the system. And from those measurements, I can do lots of things from that. Yeah?
How sort of natural is the basis? Does that make sense? Like, if
Oh.
you were starting with a new system, would you be able to apply this, come up with points, and then, like, right? Like,
Yeah.
you pick the sort of natural basis. Is that what that's?
Yeah, so here we picked essentially a tailored basis for this system. So to some extent, you can say what I just did was very fake, because I knew I had full state estimates initially to bring it down to this. However, even if you don't use a tailored basis, the architecture still will allow you to go after, like, if I use a general basis, I can still, like, just like I said, wavelets are a general basis. Compressive sensing works completely on just pick a basis. Fourier wavelet. You can compress images in any of these. And so maybe in one you have to use slightly more than another for reconstruction. You'd have to use more sensors. This is almost like the minimal number you could use. And if you used a more general basis, so you didn't have the tailored basis, you'd have to use more sensors. But still, it gets you around full state measurements, right? That's the important thing. Is a lot of these spatial temporal systems. Again, if you're in biology and you're going to put probes inside of a monkey or a rat to, like, measure activity, you don't have full state estimates. You have a number of places there, so you can try to go after those. Yeah.
One thing I was wondering from kind of the first section of the talk is how much data do you need for a particular type of system? So you're kind of getting at this here with very complex atmospheric system. Have you looked at some of the simpler models you've talked about before, and has it changed? Is there kind of a difference between?
Oh, in terms of amount of data you need?
Yeah.
Yeah, actually, the more complex you can imagine, the more you need, right? Even here, I mean, I don't know if you saw it, but check out 1997. Is it going? So all of a sudden, 97, you'll see this thing lights up with a sensor to get the El Nino mode, right? Like, pop some, so you start popping measurements on this thing, and that, right, at that point it's saying, hey, if I need to reconstruct this, I need a sensor right here to get this right. So the more complex spatial temporal patterns you have, right, you have to pull this apart in a more sophisticated way to get that kind of information. That's why the multi-resolution piece is so important for this thing.
If you go back to, does this make sense for the picture here where you have the full state?
Yeah.
Like your monkey, you've got to put these sensors in.
So in that one, you would start off with, again, it goes back to, like, having just a generic basis. You might say, like, well, in this basis, I'm going to represent everything in terms of, let's say, Fourier modes instead of anything special. Most signals are still nicely compressible in general basis, like Fourier and wavelets. So you might say, I'm going to just project everything onto one of those kind of bases. It'll still be compressible. It just won't be as compressible as if I used the best basis. In some sense, what I'm doing here is using the best basis possible because I have access to the full state to construct it. And if you don't have access to that, then you say, I'll use a general basis. You'll pay a marginal cost, so you can have to cost more sensors to do it. But you can still compress in these states. Another way to say it is this. There's an interesting thing going on with the evolution of your cameras, right? How many pixels do you think you need? Like, they're going to sell you the next phone with 4K, and then 8K, and then 16K. You cannot, right now, even hold this phone still enough to make any of that worthwhile. They'll still sell it to you. right? Because it'll still be a buck. Who cares? You can't hold it still. You'll still be like, dude, you got the new 16K camera? Oh yeah, it's awesome. It's like your hand wiggle undoes it all, okay? Here's the other question. If I take a picture of your face, you know at 4K, I got 24 million pixels of your face. I know this ain't worth 24 million pixels, right? You can go down quite a bit and you're not gonna lose anything. So this is all artificial. The 4K, 8K, 24 million, 48 million, 100 million. The dimension of my face never changed. You just give more information. What you're going after here is sort of, in some sense, the intrinsic dimension of the system you're measuring. So that's one of the problems I think also with data analysis is we can make 4K and 16K. So you just make it. And now instead of loading your hard drive with a terabyte in an hour, I'm going to load that in 1 minute. You're still going to have to process that data. And it's not clear there's any information added. In fact, I would say most information you're going to gather in data is going to be garbage. Okay. So it's the underlying rank of the thing you're measuring is what really matters. That's the ultimate thing. So, and by the way, from a lot of engineering systems, we actually inherently believe there's a low-rank structure in things we look at. When you look at eigenfaces, which are like, correlated face height, totally makes sense. You have a model in your head of going towards parsimonious representations, low-dimensional embeddings. I actually think that we have a lot of prejudice towards these things because they're interpretable and generalizable. Eigenfaces are things like, oh, that's kind of an outline of a face, and oh, those are the ears, and those are the eyes. Those are things that that's what makes a face to me. They're sitting right there. And that's really low rank compared to where it could live in pixel space, which is almost going to infinity these days. Okay, so that's one way to measure. I want to talk a little bit now about, so these are all based upon the idea of linear measurements or linear subspaces. Everything I talked about there was trying to find a linear embedding for the data. And now what we're going to do is relax that a little bit. The first part of my talk this morning, I just talked about AX equal to B, and then we started the second part of this morning's talk about, well, okay, I'm going to allow a little bit of nonlinearity by building this Koopman embedding, right? A little bit of neural nets. So what I want to do is the same kind of thing here. Is the linear model works quite well. I want to try to see if we can learn a nonlinear model for measurement space. So here's going to be the idea. I have a state space. There it is, X. And I have a measurement, S. So the measurement is a small subset of the full thing. Okay? And part of your objective, right, is you just want to learn a map from the small measurements to the high dimensional space. That's the goal. Right there. You want to approximate it with that function f. I want to learn that f so that when I take my measurement, I can make an approximation to the real x. So x hat there is trying to approximate x. So, here it is. That's the optimization. So Sasha talked about some optimizations, and this is pretty obvious. So this is your f. Like, it's easy for me to say, this is what we should do, right? That's like trivial. Like, any of us could have written this down because, like, oh, I know what you want to do. You want to, like, make sensors match the data. The regularizer is going to come next. Okay? All right. And I give you a training set to make this happen. All right. So one way to do that, and this is the way we've been doing it previously, is to build a linear map. So take that f, make it linear. How do we want to make it linear? Well, look at a low-rank subspace, and one of the best ways to get down to that low-rank subspace is through the singular value decomposition, or PCA. So you just project into a low-dimensional space. So now your measurements, your linear measurements, now it's like, hey, there's a measurement. So x takes you from your measurements, it takes you from your state space to your measurement space. And this h is just basically going to be and this thing can be expanded in terms of this low-rank basis set. So this is what I have. That's my model. And I can just do least squares on that. So this is a little bit of what I already showed you. So that's the linear map from measurements to the state space through an SVD. Okay? The nice thing about this, it's fairly cheap, right? And then you can start looking at some of this, and this again goes to Krithika's work, which is you can start asking questions about, where should I optimally place sensors in the system based upon this. So now I want to figure out, like, oh, given that map, I want to do a good job reconstruction, so I'll let S move around where these measurements are. And, if you start placing sensors in a principled way, if you have 100 sensors, this is where you should put 100 sensors on the ocean. If you have 200 sensors, you have 300 sensors versus random. And it turns out there's a big difference in performance if you just lay random sensors down versus putting them down in principled ways. And here's the performance differences. Okay? So here's what the truth is, and here's a 100 sensor reconstruction using this QR that Krithika built versus random versus compressive sensing. You can see compressive sensing doesn't do well at all. Okay, so all these methods are quite different in terms of how they're using the technology. And you can see that, this QR placement does amazingly well, whereas random and compressed sensing don't. So part of the storyline is pick the right mathematics to do the job you got going for yourself. And this is linear algebra. QR is like the oldest trick in the book in computation, in some sense, for matrix decompositions. Okay? And so we're just recycling this old idea, but bringing it into new context. And it's quite remarkable what you can do. This, again, just linear algebra. Projections. You can even change this around and start doing this, which is say, yeah, but this made me put a bunch of sensors in the middle of the ocean, right? That's expensive. I got to get a boat. I got to drive out there. I got to put my sensor down. And every time something goes wrong, I go fix it. I go drive my boat. Now, it won't be bad if you're in certain places, like I think Hawaii's right out there. Polynesian islands are here. Like, so, that could be good, worthwhile your time to go fix it. Like, oh, it's broken for another year. I'm going to have to stay out in Tahiti fixing a sensor. So maybe a company will pay you to do that. That'd be awesome. But in general, what the company wants you to do is say, like, can we just figure out a way to place these on land? Right offshore. Cost is marginal then, comparatively. And the answer is, yes, you can. So you start now saying, I'm going to solve the same problem again, but now I'm going to put a cost function on this. I'm going to make a cost landscape. And the cost landscape is going to be the following. If I have to drive a boat out there, it's expensive. If it's on shore, awesome, no cost. Okay? So you can start doing this and you solve a different optimization problem where now you bring in the cost constraint. You're trying to minimize the cost subject to the fact you want the sensors to do a good job, right? So now you have two pieces of objective functions working together, and you can control their balance with, typically a hyperparameter, some lambda, where you say, like, I'll make expensive really expensive or cheaper, and then it's going to start placing sensors in different ways. So here is a picture of what this looks like. If there's no cost constraints, this is, I think, 300 sensors. Cost is no object. This is where I'll place all the sensors. Those are the optimal locations. Now I start to penalize you and say, like, yeah, but those sensors are going to cost more and more. So I raise the cost. Here's what it does. Moves a bunch to shore, but look where it keeps some interesting sensors, right? And then I say, now I make it really prohibitive. I really spike the cost of anything offshore. Here's what puts all the sensors, all on land. And the question you ask is, okay, well, that's also got to cost me in performance, and here's the performance. You go from 2.5% to 3.3% error from going from here to here. Right? So you saved a bunch of money, and yes, you lost a little performance, but not too bad, right? So this is like the engineering solution, right? I don't have infinite money. I mean, if you're Google, you can say, let's even put more sensors. Let's have a party boat with sensors because we just have so much money. What are we going to do with it all? Most of us live in a world where that's just not the answer. So we got to actually think about cost constraints a bit, okay? Now, these are good people to work for because they'll just write you big checks. So that's not bad. I think that's as long as you're there, okay? But that's the idea of this. All linear. Now we're going to try to go nonlinear. And what we're going to do is build a neural net for a targeted application, which is learn the mapping. Again, notice what I've done with my neural nets. I let them do stuff, but in a very constrained way. I will never let a neural net be end-to-end for myself personally. It's too much flexibility of this thing. I want it constrained, so every piece it pulls out, I can still interpret. So the interpretation here is I just want it to learn a map. Okay? Just like I did before in learning a coordinate transform. So here's the mapping problem. I want to learn this F now. Remember, F is the map between my measurement space X, S to X, which is the state space. And what I'm going to do is learn a set of layers. Each one of these W's represents a neural network layer, and neural networks are compositional in nature. So this is just a composition of a bunch of layers together. Okay? And what we do know about these neural nets is that they're these universal approximators. So, you know, we know that if you give it enough data, this thing will work great. But by the way, is that really that surprising? What we know is you give me any complete basis, I can represent anything in it. So there's nothing special about this. You can do this for you. You can do it with wavelets. You can do it with almost any representation. If you have an infinite series, it will represent it. Okay? So part of what we're going after here is finiteness. Okay? And also, this gives me nonlinear functions to work with. People, I think, are really trying to understand how these nonlinear transfer functions allow us so much nice flexibility in representing functions. That's sort of state-of-the-art math, I guess, trying to understand neural networks that way. So here's the map we're going to build. It's going to be a shallow network. On one side, I give you the sensors. On the other side, I give you the full state space I'm trying to reconstruct. I give you a two-layer network. It's a decoder. It goes from low dimensions to high. And by the way, this low dimensional is these. I'm going to measure on the cylinder. I'm going to measure on the flow on that cylinder. And I'm going to have a limited number of pressure measurements, let's say here. And I want to reconstruct this whole field. Now, what I give you to accomplish this task is a set of training data, a set of snapshots of these measurements and the corresponding reconstruction. So that's what I'm going to give you to train on. Okay? And once I give you that to train on, your job is to say, like, okay, how well do I do? How well can I do that? If I train this thing, I give you new measurements, how well does it do in reconstructing that flow field? And now, the only thing really that I did before, what I did in here before, I just built an SVD map, right? I just said, take the SVD of the data, project down, and that's a linear map, and now it's nonlinear, okay? But the nonlinearity now gives you some flexibility. So it's a two-layer system. Here it is. You know, you go from one layer to the next. It's compositional in nature. And typically, what you're going to determine is some weights and some biases on each layer. It's a standard thing in neural networks to go after. You can think about some different activation functions. Here they are. You can do a ReLU, swish, soft shrinkage. These are all different nonlinear possibilities. By the way, all these activation functions are picked for one reason, right? Or because they're easy to differentiate. When you do backprop to train this thing, you're going to do a gradient descent. You've got to take derivatives of these functions. Super awesome derivative to take. 0, constant, right? You set these things up so that that's how easy it is, right? So a lot of these functions are just basically picked because they're super easy to differentiate. In other words, you differentiate them by hand, and so you say, like, oh, the differential of this activation function is this, so you just put that into the computer to update the weights of those functions. Okay? So how do we do? Well, it's interesting. You get some really interesting results out of this thing. And here you go. Here's what some snapshots look like to train. Here's your shallow decoder. So one thing you could do is I'm going to compare the linear versus the nonlinear mapping. Now, the linear mapping is working with these set of modes. These are the proper orthogonal decomposition modes, PCA modes, SVD modes, whatever you want to call them. That's the linear map that we talked about previously. And you can see this is what it looks like. These are the modes, for first 4 dominant modes. What's interesting is if you look at the output layer of this thing for the first 4 dominant structures out of this nonlinear map, it produces structures like this, which is interesting because when you look at the flow field, this is kind of more what it's doing. If you try to reconstruct the flow around the cylinder, which is these periodic vortex shedding, you have to add it up in your mind. You could look at these and say, like, well, if I added them just right with just the right frequencies, you could imagine it being an oscillation that sheds vortex off both ends periodically. But here it's like it's got the actual structure in there already. Okay? So that's kind of an interesting thing you find from this, because those are your sort of modes that really come out of this thing that are of highest interpretability. And you can also find that it basically gives you quite better performance compared to the linear map. So here's the true spectrum is in black, and then your shallow decoder actually hangs onto it for quite a bit longer than your linear mapping does. Okay, both on the training and the validation data. Okay, so there's some reasons you might want to go with this nonlinear map. Another thing that I think this is the one that, frankly, is the most convincing to me, and why you might want to use this. You start saying, okay, now I have noisy measurements. This is the case you're going to have to live with in general, right? Is that you're going to have to figure out how to handle noise, no matter how anything goes down in your life. If you're going to engineer a system, the only way to avoid noise is to do pure math, where you can just make assumptions that there's zero noise, right? And then work some paper magic. But the minute you say, I want to go work a real problem, you got noise, and maybe way too much. But here's the interesting thing. I'm going to take measurements right there at those orange dots. I've learned the mapping. I take measurements there, but they're noisy measurements. And in fact, here's the field. This is the noisy field that I actually measure right at the cylinder. I say, okay, if I use this linear map, what's my ability to reconstruct the truth? Well, here's what it does. This is the linear approximation to this. If we modify this, although we found a technique to modify the linear measurements, we can do a little bit better. But if I use this nonlinear encoder, check it out. You nail it. Much more robust to noise. This thing here can tolerate that amount of noise and actually get back what you're supposed to get back in the system. Okay? We did some comparison, blah, blah, blah. Okay, so here, those black dots, that's where I measured ocean temperatures. Here's the reconstruction. So this is, the truth is underneath there, right? So, but then here you go, that's the comparison that you have. And there's not that many sensors out there, like maybe 50, right? And we didn't even optimize the placement, right? We just simply said, take these 50 locations and measure them. How well do you reconstruct the full state? And this is how you do. So really powerful and flexible architecture off this nonlinear encoder. One thing that's still outstanding is where would you place these sensors, right? It was a lot easier in the linear model to figure out how to optimize and place sensors. I say like, oh, well, if I have that information, then I should say, I shouldn't do this. I should say, where should I put them to do the best job possible? We didn't do that yet, because now you have a nonlinear problem on top of this, which is really difficult. And the other thing that you can do is this idea of what's called super resolution analysis. Here it is. In a lot of systems, this is the kind of results you would measure. And this is a low resolution version of that. And you can see how much detail is smeared out. Now, this problem, I think, is extremely important for two reasons. One is often the coverage that you would have in a network of sensors would give you this kind of picture of your system. Okay? You'd really like to reconstruct what the truth is. So there's a question of how could I do this and get that back? Again, even in the compressive sensing framework, you could frame this as an AX equal to B with a subject to line or a regularization that would allow you to go towards some of this. Here, we'd like to try to use this network architecture to take this image and reconstruct it. And by the way, here's what it gives you. So you could see I did a pretty great job with it. Now, this is important not only for a sensor network, But even if you're going to solve, let's say, code at scale, we just had a physics-informed machine learning workshop on the 6th and the 7th here on campus. And one of the plenaries was Michael Brenner. And he talked about this problem in some sense, which is when they do simulation of atmospheric dynamics, their grid cells are massive. This is kind of what they simulate in a PDE model. That's the resolution they can do. Just because that's what they can do. You know, they'll build better machines, bigger machines, more and more, and they'll refine this. But right now, state of the art is, that's what your simulation's giving you. So you can't even see stuff like this. So what you really like to do is find a way to say, well, if I can learn this map from the coarse-grained simulation, which I can do sort of in real time to do forecasting, I could come back in and fill in, let's say, the microscale dynamics, because I've learned to map back to that thing. So these are all these tricks that are just data science. They're just optimizations. They're just AX equal to B's or slight modifications of nonlinear versions of AX equal to B with subject to lines or constraints on them. But they all kind of highlight to the same thing. So, you know, the conclusion on this becomes, you know, like I said, we went backwards in the sense that your first point of contact with data is going to come through your sensors. So right away, the sensor problem is probably your most important from a practical level. And then you go up to finding, like, well, I'm measuring something. I should find the right variables or coordinates, and then I should try to do model discovery on that. That's kind of the pathway. But this gives you a really nice sense of how, you know, and again, I think there's some really simple math you can exploit. Not all of this is, in fact, very little of it. If you notice, 90% of the time I focused here was all on linear algebra techniques. And the key to it working was just imposing a regularization on that linear algebra. And that's it. You don't have to get into this like, oh, they got this deep neural net doing this, that, and the other. Like, I can get a lot of mileage out of this thing and interpret it just on linear algebra. So there's a lot of life. And part of the reason we don't think about linear algebra being that powerful goes back to what I said earlier, which is we learn linear algebra as n by n's. And that's not what's going on here. What's going on here is tall, skinny, or short, fat. You are in situations where you're massively over or under determined. Your key piece of thing that you got is this leverage point around imposing a regularization or a constraint. And that is the magic that happens. And now you can take linear algebra to a whole new level. Okay? So, and part of the reason I highlight that again is this is accessible to people. This is not like I gotta go learn a bunch of extra stuff. This is like, do you know linear algebra? Do you know a little bit? It's linear algebra. Okay? So I want that clear, is that the entry point is not some mountain you got to climb. The entry point is right now. You right now can enter and start thinking about these things and doing fairly sophisticated things with an entry point of AX equal to B. Okay? A couple of final slides, overview to just cut this thing off here in the last couple minutes. There's a diversity of strategies out there. The other thing I'm going to say is that if you notice, we covered a lot of different things, from DMD, Koopman, to Cindy, to sparse measurements. They all have a very similar architecture that glues together in many ways. The thing I'll say is that I'm going to come back to the first slide, which is the first slide of this morning I said is, what's the nature of your data? And what you're going to do in terms of methods should be determined by the nature of your data. In other words, you shouldn't walk out of here and go, I really like that Cindy. I'm just going to go use Cindy on my problem. The first thing you ask is, what's my data look like first? Then I'll pick a method accordingly. So I give you here, this is a very rough, just think, this is a cartoon, but it's, I think, an important one. I give you 3 axes. Noise, so this is the quality of data, where this is really bad data, because it's got a lot of noise on it. Quantity, how much data do you have? Observability, what are you actually observing? And what I give you is all these different techniques that exist. If you have really noisy data and very little of it, you use DMD. you trying to use all this other stuff is worthless. You don't have enough data for it. Nor is it clean enough. If you have a lot of high quality data that's clean, neural nets are going to be pretty good for you. And there's a lot of stuff in between. From Cindy to Koopman, these are called Havoc and Mori Swansek. These are time delay embeddings, stuff we didn't talk about. But anyway, I think the thing is don't commit up front. You shouldn't be committing to a method up front. You should commit to a method after you understand your data. Okay? If there's one take home, I hope that is part of one of the take homes that you get out of this is try to evaluate what you got, pick the method appropriately. And I know you might want to use Cindy, or you might want to use this neural network, but the question you have to ask is, does it even make sense given the nature of my data, right? Or is it just completely gratuitous? It's easy enough to just throw stuff into code and just run it. But making informed decisions really matter. The other thing I want to highlight is that we are living in this age where I drew this data pipe as sort of big out here. It's just getting bigger and bigger. Like I think people have the attitude, which is I'm just going to collect more, better sensor. It's just collect more, right? And very quickly you get into this situation where, are you gaining anything? Like I said, I think the camera is a perfect example. If I just take higher and higher and higher resolution, at some point it's like you didn't gain anything except for you loaded my hard drive. And now I can't even read the information because now I need like a computer science expert who knows how to run Hadoop because I just want to pull in a little bit of data and I need an expert just to pull in the data, right? And the question is there anything in that data in the first place, right? These are issues I think we're going to have to face as a community because it's cheap to make sensors that just pull in more data. I mean, that's dirt cheap. And the question, but it's not clear there's anything gained by it. So once you get this, you need an ingestion architecture. You need, I've talked about sparse sampling. This is really important. Like you shouldn't measure the whole thing probably. Pick the pieces that you can measure, make use of them. Figure out where they should be. Then you can do some model discovery. And the bullet here is, I think, is an important one. Not everybody's going to get to this with a lot of the applications, but in a lot of applications, the end goal is control. If I understand my system, I'm going to build a system that I can architect and control. So I first have to figure out what the model is, figure out how to get the data in here, learn a controller, and all these feed back on each other. What I learn here, I can then say, oh, given this, I should actually measure over here, which builds that model better here, which then gets me a better controller. This is all wrapped together in some kind of, to some extent, I'd say the meta learner that sits on top of all this is some uber learner that is just taking information in and updating its models. Say like, I had this data stream, but when I learned this model, I figured out a better way to measure this thing. So now I got even a better model, and it's improving itself through time. It's taking night courses. You're never too old to learn kind of thing. Lifetime learner. That's what we want to build is lifetime learners. Okay. Okay, this is a little gratuitous. I'm sorry, but I'll just put it out there. I have a number of books with Steve. The most important thing I want to highlight here is these books are out there, but everything's up open source. We have a ton of videos. If you want more details on some of this stuff, ton of YouTube videos. All the code I talked about, everything here is all open source. You can download it. You can start working with it today. Simple examples between MATLAB, Python notebooks. You can find most of it here just by linking off of my page and going to, there's a little tab there, open source lectures. And you can go there and you can get this stuff and you can pop out like data and code and immediately start playing with this stuff. We've worked really hard to try to make this as easy to use as possible. And also we are very aware that okay, maybe some of you have known me from before. Maybe this is the first time you've seen me talk. So you've just learned some of the stuff for the first time. But at the end of the day, this stuff is like a learning process over a long period of time. So being able to come back to stuff when you're ready for it, this is partly why we set this up this way, and also having the code out there so that it's completely transparent for everybody. So I'd encourage you, if you have any interest in this direction, a lot of resources out there. And we also point you to a lot of other resources that you should read, papers, so forth, that we think are particularly good for you to think about a little bit. Dang, you had to listen to me a long time. Sorry about that, but enjoy your lunch, and see you guys the rest of the week, I guess. Yeah.